You know those tiny little computer brains that are hidden inside, well, pretty much everything these days? Your keyboard, your coffee maker, your car, they're literally everywhere. Today, we're going to crack one of these open, metaphorically, and see exactly how it thinks.
What you're looking at here is an STM32 microcontroller. These little chips are some of the true unsung heroes of our modern world. They're the things that translate our digital commands into real-world actions. And while they're super common, how they actually work, well, that's a really fantastic story.
And that's the big question, right? That's what we're going to answer. We're about to go on a journey that starts at a programmer's keyboard, goes deep into the silicon heart of this chip, and ends with a single, simple blinking LED. It's a journey from pure code to actual physical light.
Okay, so before we can really dive into our specific chip, we need to zoom out a little and look at its family tree. It belongs to a huge and really diverse lineup of processor designs from a company called ARM. And trust me, you've definitely used their technology, probably without even realizing it.
So this Cortex family has three main branches. You've got the A series, think big application processors for things like your smartphone. Then there's the R series for real-time, ultra-reliable systems like the brakes in a car. And then, our focus for today, the M series, which is built specifically for these little microcontrollers.
And this really gives you a sense of that incredible scale. I mean, you've got these massive, super fast processors on one end, and on the other, you have these tiny, incredibly efficient cores like our Cortex-M. ARM really does have a blueprint for just about any computing need you can imagine.
All right, let's zoom all the way in. We are now inside the processor core itself. And to really get a handle on how it operates, let's imagine it's a surgical team working in an operating room. It's a fantastic way to picture what's going on.
Think about it. A surgeon can't just perform a delicate operation on data that's, floating around in general memory. No way. They need a dedicated, super high-speed workspace, an operating table really, with very specific tools laid out. For the CPU, these tools are called registers.
Now, have a look at this. This diagram right here, it's essentially the CPU's entire surgical tray. These registers, R0 all the way to R15, are the only places the CPU can actually perform its calculations. Any piece of data it needs to work with has to be brought to one of these spots first.
Let's meet a couple of the key players on this team. Register 15 is called the program counter, and you can think of it like the lead surgeon's finger, pointing to the very next step on the procedure list. It just relentlessly moves from one instruction to the next, keeping the whole program flowing in perfect order.
And then you've got Register 13, the stack pointer. This one is like the scrub nurse, carefully managing the tray of temporary tools. Every single time your code calls a function, it uses a temporary storage area called the stack. And the stack pointer's job is to keep track of every single thing put on or taken off that tray.
And hey, speaking of the stack, it's one of two main ways a CPU handles memory. The stack is like that little tray right next to the surgeon. It's incredibly fast, it's automatic, and it's perfect for temporary stuff. The heap, on the other hand, is more like a big supply closet down the hall. It's bigger and more flexible, but slower. The key thing here is that using the wrong one can cause big problems, like a stack overflow, which is literally when you try to put too many tools on that small, fast tray.
Okay, so the CPU has its internal operating room, its toolkit, but how does it actually talk to the outside world? With memory or with physical hardware like our LED? Well, to do that, it uses a brilliant system that's kind of like a giant building filled with magic mailboxes.
I absolutely love this analogy. The CPU literally sees its entire universe, all 4 gigabytes of it, as one giant wall of mailboxes, and every single mailbox has a unique address. What happens next depends entirely on which mailbox you choose to interact with.
And here it is. This is that apartment building. This is the Cortex-M memory map. You can see down at the bottom, you've got mailboxes for your actual code living in flash memory. A bit higher up, you got SRAM, which is where you store your variables. And then you get to this special section for peripherals. This, my friends, is where the magic happens.
This whole concept is called Memory Mapped I/O, or MMIO for short. And here's the kicker. To the CPU, writing the number 1 to a mailbox for a variable is the exact same operation as writing the number 1 to one of these peripheral mailboxes. But in that second case, the mailbox isn't a storage box at all. It's physically wired to a pin on the chip. Writing to it doesn't just store data, it physically flips a switch and turns on an LED.
So now we have all the pieces on the board. we've got the CPU with its registers, and we have this memory map full of magic mailboxes. So let's see how they work together to finally do what we came here to do, blink an LED.
So if we want to do this directly, using those magic mailboxes ourselves, there are 3 basic steps. You can't just start talking to a pin. First, you have to turn on the power to its entire department. Then you tell the pin what its job is for the day, and only then can you actually give it a command.
So here's the code for that first step. And I know, it looks like alphabet soup, right? But stick with me. All this line is doing, and I mean all it's doing, is putting a very specific number into the magic mailbox that controls the power for what's called GPIO port A. Think of it as just flipping the main circuit breaker for that section of the chip.
And then, after telling the pin what to do, this is the final command. We write another special number to the output data register for port A. And because that specific mailbox is physically connected to pin 5, boof, the voltage on the pin changes and our LED lights up. It is literally software causing a direct physical event.
Now, all that register math is super powerful, but let's be honest, it's pretty complex. And that's exactly why chip manufacturers give us a helpful shortcut. It's called a hardware abstraction layer, or HAL. This single readable line of code does all of that complicated mailbox business for you behind the scenes. You might trade a tiny bit of performance, but for most projects, hiding that complexity so you can focus on what you want to do instead of how, well, that's a massive win.
So, our LED is blinking. Mission accomplished, right? Well, not quite. We've actually skipped the very, very beginning of the story. What happens in that split second right after you apply power, but before your own code even begins to run? Turns out, quite a lot.
This is what's called the reset sequence. You can think of it as the chip's unchangeable, hardwired boot-up checklist that it runs through every single time it powers on. It's this beautiful, precise dance between the hardware and some very low-level software, all designed to get the chip ready to run your code.
The whole thing happens in a flash, and it boils down to these 4 key steps. The hardware figures out where its temporary workspace is, the stack, and then it finds the address of its very first instruction. After that, a tiny bit of code wakes up the system clocks and gets memory ready. And only when all of that is absolutely perfect does it finally hand over the keys and call your main function.
So at the end of the day, it's all about this. A microcontroller is really just an incredibly fast machine for writing numbers to specific addresses. Some of those addresses are just for storing data. But the really interesting ones, those magic mailboxes, are your direct line to the physical world, turning lines of code into light and sound and motion. The only real question left is, what will you build with them?